Good morning and welcome to the conference Transforming Higher Education, Digital Skills for a Digital Future. My name is Chris Cartwright and I am the chair of the digital panel at the Institution of Engineering and Technology. I'll be with you throughout this conference, greeting you, guiding you and putting your questions to our panelists. Today is the Academia Day for the conference, looking at what higher education is doing to transform itself to create digital skills for a digital future. This conference is brought to you by the Institution of Engineering and Technology, whose aim is to inform, inspire, and influence the global engineering community and support technology and innovation to meet the needs of society. In today's session, we'll be doing just that, aiming to inform, inspire, and influence some of your teaching practices in higher education, or some of the education partners you work with. First, we'll be hearing from OpenSTEM's lab at the Open University with Dr. Helen Lockett, followed by a short break, then for a lecture from Dr. Freeha, who will discuss degree apprenticeships. We'll then have another short break and we'll conclude with Professor Mehmet Karamanoglu and Luke Bennett from Middlesex University, who will discuss some of the digital tools they've been using to teach students because of COVID-19 restrictions. Please do contribute your thoughts through Slido with the hashtag IET Digital Skills. I will be taking questions after every speaker for our live Q&A, and the most popular questions will be asked. So please do vote up your questions as we go through. Questions will be refreshed between speakers, and please do not be disappointed if your questions are not answered. However, if you still want answers, please feel free to contact sep@theiet.org, who will be happy to find appropriate members of staff to answer them. Before I move on to our first speaker, please be aware that tomorrow is our Industry Day, of which we will be talking with industry partners about how they are supporting higher education to transform itself to create more digital skills for a digital future. With no further delay, I wish to thank you for attending and hope you enjoyed the presentations. I would first like to welcome Dr. Helen Lockett from the Open University. Helen will be introducing the Open Engineering Laboratory, which is part of the Open STEM Labs, which delivers practical learning at distance for STEM students at the Open University. Please remember to ask your questions on Slido using the hashtag IET Digital Skills and vote up your favourite questions. I will be asking several of them directly to Helen at the end of the presentation. Thank you, and over to you, Helen.
Hi, my name's Helen Lockett. I'm the director of the Open STEM Labs at the Open University, and I'm a senior lecturer in engineering. And today I'm going to be talking to you about using remote laboratories to support practical learning in engineering distance education. It's great to be talking to you all today, and I'm really sorry that we're not all in the room together. I also just wanted to remind you that if you'd like to ask me any questions, there'll be a Q&A at the end of this session, and you can ask your questions using Slido. I'm going to start by giving you an introduction to the Open STEM Labs, which are the way that we deliver practical learning at a distance to our distance learning students. And then I'm going to focus in on how we deliver remote experimentation to our Open Engineering Lab students. I want to show you some example activities, and I'm going to try and demonstrate one of the activities live for you. Then I want to reflect a bit about the opportunities and challenges of remote practical learning. So thinking about what works well and what's difficult in that situation. And in particular, I want to focus on some of the challenges we've all had this year with the COVID-19 situation. And then I'll finish up by telling you a bit about how you can access some of our resources yourselves, and some of them are available for free. I'll finish up just with a summary. So I think we all know very well that practical learning is an essential part of many STEM subjects, and students usually spend a lot of time in the laboratory with the staff and students co-located together. Of course, that's quite challenging this year with the COVID situation. The Open University is a distance learning university, and we've got more than 50 years experience of delivering practical learning at a distance. And we've had to come up with different ways of delivering that practical learning. In the early days of the Open University, we used to send home experiment kits. So if you were studying chemistry, you would be sent a chemistry set and the chemicals. In biology, perhaps a microscope. And in engineering, computing kits, robotics kits. Obviously, as technologies have developed, we've moved into using digital technologies to support the way that we deliver distance learning, and that's where the Open STEM Labs grew. It's worth also mentioning we still do some face-to-face learning with our students. So engineering students still attend residential schools for a 1 week intensive period twice through their degree. But of course, like everybody, that's been a challenge for us this year. So I wanted to tell you a bit about this Open STEM Labs concept. We use remote and on-screen laboratories to deliver practical learning to our Open University students. And we have activities in bioscience, chemistry, engineering, physics, and astronomy. And all of the activities work with the student interacting with the experiment via a web browser on their laptop or their mobile device. So the picture on the right gives you an idea that the students connect to our Open Science or Open STEM laboratory, and they can see all the activities that are relevant to their course, and then they can just click to access an activity. And most of our activities are available via a booking system and up to 24 hours a day, 7 days a week. So students can undertake the activities at a time that's convenient to them. But within that Open STEM Labs concept, we have a number of different ways that we deliver our practical learning. So the first way, if you look at the slide on the right, sorry, on the picture on the left, we use remote experiments. So a remote experiment is where a student is connecting to a real physical piece of equipment, usually located on our campus in Milton Keynes. So you can see on the left-hand side here, there's a pressure vessel, so that's sitting in a lab in Milton Keynes, and the student is controlling that equipment and interacting with it through their web browser from home. So we call that a remote experiment. Some of our activities are on-screen experiments, so that's the one in the middle. So this is where they're engaging with real data. In this case, it's a virtual microscope. So it's real scanned microscope slide, but they're engaging it with through a simulated environment. So in the environment, they can set the magnification, they can set the focus, they can set the lighting, but it's a simulated software environment that's letting them engage with real data. So we call that an on-screen experiment. Lots of people will call those virtual experiments. And if you kind of compare and contrast the two, on-screen experiments are great because they're infinitely scalable. So we could have 10,000 students all using the virtual microscope at the same time. Whereas for the remote experiments, you need a piece of equipment for each student. So you have to be much more careful about resourcing. I think perhaps there's also an element that students really like the reality of a remote experiment. They like to see that they're using real equipment and the issues that you face by using real equipment. So remote experiments and on-screen experiments are usually for an individual student or maybe a small group of students working together. And if we want to deliver practical learning to larger groups, we use a concept called labcasts. So that's the one on the right-hand side. And you can think of this as kind of a laboratory demonstration. So in a conventional environment, the tutor's at the front of the class demonstrating something and they have a room full of students. So we have a laboratory that's got a nice set of cameras installed in it. And the tutor is at the front of the room delivering their presentation to a group of people who are online. But we try to make it as interactive as we can. So we'll have multiple camera setups on the demonstrator, on their hands and what they're doing, directly on the specimens. Students can engage with the chat to ask questions, and we use voting pods and things to try and make it interactive. So labcasts are great for larger groups. And in the Open STEM Labs, we use a combination of all three. I wanted to tell you a bit about the principles that we build the Open STEM Labs on. So we have this kind of overarching aim to provide authentic, online, practical experience to enhance student success in STEM subjects. And all of the activities are built on 4 kind of principles. So we want all of our activities to be inclusive, to be accessible at any time, from any place, by anyone. All the activities are built on the Open University's distance learning pedagogy. So we build into them the individual or group working style, and we have all the activities in the context of either a student-led or a tutor-led inquiry. And we want the activities to be interactive and collaborative. I mentioned before the importance of real data. So we have a concept of veracity. The students are always using real data. And for the remote experiments, they're using real equipment in real time. And finally, we want the activities to be authentic. We develop bespoke teaching tools, but also use industrial grade equipment and research grade instruments. So our students will be perhaps using a scanning electron microscope remotely, using our observatories and telescopes remotely, so that they're really using industrial grade or research grade equipment. And a few facts and figures about the lab. It's really well embedded now in our faculty. So 46 of our taught modules use the Open STEM Lab. And in those modules, about 100 different Open STEM Labs experiments have been developed. And we have something like 10,000 new users come through our lab every year. So it's really quite a large operation. We've won lots of awards. I can't claim any credit. Most of them were won before I was involved in the labs, but we've won Times Higher Education Awards and Guardian Awards for our innovative teaching, and also international awards for the lab work. So the Open STEM Labs is really an umbrella for a number of different activities, and I wanted to use this figure just to try and tell you a bit about the background to the labs and how they were developed. The lab started with the Open Science Lab in about 2013, and we got funding from the Wolfson Foundation to develop the Open Science Laboratory. So predominantly that was working with bioscience, chemistry and physics. And alongside that, we developed the Open Science Observatories. So astronomy students at the Open University can use telescopes that are located on the island of Tenerife to observe in one of the best locations in the world while sitting at home in their living room. So if you're studying astronomy with the OU, you can be observing the sky in Tenerife from your home. In 2015, we planned to expand the labs into the engineering field, and we applied for funding to the Higher Education Funding Council for England and had a really good investment of money to allow us to develop an engineering wing to the lab. And then the final part of the lab is our on-campus laboratories. So I mentioned that students still do residential schools. So in the chemistry field, they come onto the Milton Keynes campus to do chemistry day schools. And the on-campus labs are also where we host our labcasts. And the pictures around the outside of this figure are trying to show you that students are sitting at home, interacting through their computer, and they're both controlling things in the labs and they're receiving data from the labs. So it's all about making sure that it's a really interactive experience. So the main purpose of my talk today is to talk to you about the Open Engineering Laboratory. So as I say, this is a more recent innovation for us, but we've really strongly embedded it into our engineering curriculum. So the Open Engineering Lab provides practical lab-based teaching at a distance, and it covers mechanical engineering, electronics, control, materials and robotics. All of the labs broadly are set up the same way, that we have laboratory bench equipment that's accessed in real time by the students from home. When the labs were developed, we put a huge amount of effort into making ultra low latency. We want this instantaneous experience. And when I show you the demo, maybe that will become clear. But if students are trying to control a piece of mechanical equipment from home, it's really important they don't click the button and have to wait a few seconds before something happens. If they're in control, they need to have instantaneous control. We design the experiments so students explore and learn as if the equipment was on the bench with them. We try to build in as much of the face-to-face experience as we can from a remote activity. And we have capacity for over 300 different bench stations, all available simultaneously. And it's maybe worth looking at the picture on the right-hand side, because what you see is that a lab that's developed for remote use looks completely different to a lab that's developed for student face-to-face use. So you can see that we have racking systems, we'll have many setups of the same experiment all laid out at the same time. Each one will have video cameras pointing at it. So when the student connects, they're connecting to that individual system and working with it directly. And we use video and data streaming from our test grade engineering rigs to undertake the experiments. So maybe it's better to show you a few examples rather than to talk too much about the theory. I picked just 3 of our engineering activities just to give you a feel for the way that they operate. So this first one is broadly in the realm of mechanical engineering, and our engineering students undertake this as part of a second level module looking at stress analysis. So they're learning about the stress and strain in the walls of a pressure vessel, so kind of the equipment you can see on the top right hand corner. And in the module materials, they're learning the theory of how to calculate strain and stress in pressure vessel walls based on the pressure inside. It's quite complicated analysis, and perhaps it's a little bit abstract, and it's hard for students to visualize that this is quite dangerous equipment, and if the calculations are wrong, we could have serious consequences. And we thought it would be a great activity for the students to go through to learn about the physical behavior of the pressure vessel so they could see for themselves. So if you have a look at the activity the students undertake, I just got a screen grab from it. If you look at the image in the top left-hand corner, that's a piece of off-the-shelf student pressure vessel experimental equipment that can be bought. Probably lots of universities in the UK have them. You can see there's a cylindrical pressure vessel and it's full of oil. And in the conventional lab, a student uses a hand wheel, turns a hand wheel to force more oil into the vessel. They set the pressure using a mechanical pressure gauge, and then they read strain values. So there are strain gauges through the walls of the pressure vessel, and they read the strain gauge values to see the strain as a result of the increased pressure. So we've adapted this experiment so students can do it from home. So maybe you can see in the picture in the top left, we've attached an electric motor where the hand wheel would be, and we've given the students control of that motor so that they can drive it forward to force more oil into the cylinder or backwards to release the oil from the cylinder. We've given them a separate video camera looking directly on the pressure gauge because we want them to set the pressure using the mechanical gauge the same that they would in a face-to-face environment. So they need to have a really good view of it. And then they can learn things about taking care to set values, the fact that the pressure might settle a little bit after you've set it. And then in the bottom right-hand corner, we're continuously showing them the values on the strain gauges. And there's a little map saying where the strain gauges are through the thickness of the wall. And in the activity, the students will go through the steps of setting the pressure to different values, recording the strain at those values, and then downloading that data and analysing it. So we can teach them about taking repeated measurements and looking at uncertainty. We can teach them about logging data. So that's an example of a very structured activity that students do at second level. The creep experiment's a slightly different way of engaging with the labs because this is a purely observational experiment. And it's interesting that actually it works very well, although it's quite simple. So we set up a standard creep test, so a sample in tension in a heated environment. And we run it for a week, just with a camera watching it continuously and reporting to the students the sample extension, the elapsed time and the temperature. And we set the students the task of going in periodically through the week to observe the specimen and see how it's progressing and take data samples, and then to do some analysis. And they learn about group work because what they find is their own data isn't enough to have a good definition of the strain that occurs in the sample. But if they collect the data from a whole group of students, and we have several hundred students doing this, then they get much more accurate results. So they learn a little bit about data collection. The other thing that we didn't really expect is that there's this great jeopardy of when it's going to break. So we found that lots of students were logging in lots of times towards the end of the week, because what they really wanted to see was catch that moment when the sample broke. We do also capture a time lapse so that they can all see it afterwards if they want to. The third experiment I wanted to show you was the Fourier experiment. So this is from our electronics activities. So the purpose of this experiment, the students are learning about waves and signal processing, and they're learning about the effect of sampling rate on signal processing. So what you can see in this activity is that we have a cardboard disc that spins up on an electric motor. And then we've got 3 light sources along the top above the disc and 3 light sensors at the bottom of the disc. And essentially, as the disc spins, the slots cut in the disc mean that we can generate a square wave. So I thought it might be nice to show you this activity and show you how a student would engage with it. So let's see if we can get that to work. I'm just going to click to get us into the experiment. So this is what a student would see if they were engaging with our open engineering lab. So in the module materials, they would be directed to the lab at a certain time. They're told at the beginning of the module when they need to do the lab, and we've run a booking system so the student can book their slot well in advance, and we can offer slots all the times of the day and night, so students can pick a time that's convenient to them and maybe fits around their work and their family life. I'm in a test system, so I can go straight in. You might have seen the system always does some system checks to check that the student's web browser is suitable and that they can stream the video correctly. So I'm now live in the laboratory. It might just look like a screen grab at the moment, but this is a live video feed onto the piece of equipment that's been allocated to me. And typically for an activity like this, we might have several hundred students on the module and maybe 10 or 20 sets of equipment set up in parallel. The students are booking a slot and then allocated one piece of equipment. So I want to try and convince you that it's real. So maybe I'll just turn the volume up on the background. Hopefully you can hear a bit of background noise, so that's just our lab. I'll turn that down for the moment. So I'll just talk you through the things that the students are going to see in the activity. So first of all, we've got the equipment set up in the top left, a live video feed. We've got a control that they can set the speed that the disc will spin. And they've got some controls to do with the sample collection. So they can set the sampling rate and the number of samples. And then on the right-hand side, we've got some data visualization once they've captured the data. So I'm going to try what the student would do, which is starting to explore how to use the lab. I'll put the volume up, not too loud. I've been told it comes through very loud. So I want to just drag the slider to spin up the disc. hopefully you can hear changing tone as the speed changes. And I hope you got that idea as well. That it was very instantaneous. I drag the slider and I get an instantaneous response. So having switched up the volume, I'll turn it down while I'm talking. So a student doing the activity, first thing they might do, will spin up the disc. Doesn't feel quite so real without the sound, does it? So you can see the sound's quite important. But we've got the disc spinning at 60%, and the student might use the default sampling rate and number of samples. And what we see is that we get a square wave. So remember, the disc is spinning when the sensors see the light, we get a signal. When the sensor doesn't see the light, we don't. So we get this kind of square wave. But the student sees they've only collected 32 samples. We don't have enough data really. So now they're told to explore how to improve the data collection. And maybe I should say in the bottom right, we've got the time domain, and in the top right, we've got the frequency domain. So a student might say, well, let's collect 500 samples this time. And we can see in the bottom right, we've got a lot more square waves. But if I zoom in, we still don't have any more data points per wave because it's the same speed and the same sampling rate. But we've got more data in the frequency domain now. And then finally, well, then they might say, I want to now increase the sampling rate too. And let's do it to a final time. Just need to reset the zoom. So this time when I zoom in, we've got many more data points per square wave. We've got better resolution in the frequency domain, and we can see the main frequency and then the harmonics. And the students would go through an activity on a different page on the analysis page. I won't do it for you now, but they go through an activity to show how the various sine waves of the different frequencies build together to make the square wave. So I hope that gives you just a little bit of insight into the way a student would engage and the fact that they are really engaging with physical equipment. Let's just turn the motor off. So for a student doing this activity, they would get a 50-minute slot and they can do as much as they like in that slot. At the end of that time, there's an automatic self-check and then it's allocated to a new student, and students can book another session if they want to. Okay, so having shown you some of the activities, I thought it would be nice to reflect a little bit on what are the opportunities and challenges of this way of working. I think thinking about the opportunities, we found it's a really great way to bring alive online learning. We work really hard to make our distance learning as interactive as we can, but live experimentation brings another level to the students of feeling engaged with doing engineering. We feel it develops the students' skills and enhances their employability, and particularly for distance learning students where they might not get other opportunities for that. That's a really valuable thing that we're trying to build up more. Of course, the delivery is much more flexible using a remote experiment than it is in a face-to-face lab. It can be done at a time that's convenient to the student. They don't have to come in and to a timetable session at a specified time. And the other thing that maybe you wouldn't think of at the beginning is this maximising the equipment utilisation. Normally, university experimental equipment is only available during the timetable sessions when the staff are there, but our equipment can be available at any time that the student wants to use it. It means we're getting much more use out of the equipment we're buying. In terms of challenges, well, it is quite a challenging thing to do. The remote experiments that we've built, it's really quite costly and time consuming to develop them. And we do it with quite a large team. I guess the size of the Open University cohorts means that we have the ability to build these complex experiments. But the team of people who develop one would include the academic staff, technical staff, computer programmers, user interface designers, learning designers. So it's really quite a big group over a long period to develop an activity. Something else we've learned is about the learning outcomes, that you have to be careful not to design some of the learning out of the activity. So there's a tendency to automate, but the more you automate, maybe the less interaction the student can do. So a nice example might be to think back to that pressure vessel activity. By making the students do some of the tasks in quite a manual way, the data collection, recording in a logbook, using the mechanical gauge to set the pressure, it engages them more with the activity, actually enhances their learning outcomes compared to digitizing some of that. And the final challenge we have is making sure that our instructions are really watertight, because the students are undertaking these activities on their own, potentially in the middle of the night, and they can put a comment on a forum to ask for help, but they won't get help immediately. So we really work hard to get the activity instructions as good as they can be. I wanted to reflect a little bit about our experiences over the COVID-19 pandemic period, because like everyone, it has given us challenges. I think the Open Engineering Lab, it of course gave us a benefit over face-to-face teaching. We were already set up, and I know a lot of people were scrambling to move online very quickly. So we were able to keep any activity or experiment that was already online available through the pandemic period. So the day that the campus closed, if a piece of kit was up and online, we tried to keep it online. We built in automatic equipment checks to all of our online experiments, and we did it really to support the overnight and the weekend periods. But suddenly we found we needed to be able to use that to support for 3 months. And I think we surprised ourselves how successfully we managed to keep things going. Of course, the technical staff were working from home, and they could resolve some of the things by remote access as well. To give you a bit of an example of what was running in the Open Engineering Lab, we had 24 experiment setups that were online the day that the campus closed, and they were providing more than 500 experiment instances a day through the whole of the lockdown period. And we lost very few pieces of equipment in that period. Of course, the challenge was that we couldn't put any new activities out. And what we tend to do is to swap the equipment out through the academic year as the experiments move on. And we weren't able to lay out activities that were due to run in April or May or June. But fortunately, there weren't a huge number of instances of that. And then the thing that we didn't expect was that we had a really significantly increased number of users in the lab in 2020. So the graph on the right is showing the total number of Open STEM Lab users for about a 6-year period. And through 2016 to 2019, we've typically had about 10,000 users a year. But in the 2020 period, the blue line shows the start of 2020. We've had something like 16,000 users already this year. So it's a 60% increase. And that's a mix of more of our own students. We moved some things online that weren't usually online, but also more external users to the lab. So before I finish, I thought it'd be nice to show you how you can access some of our resources if you'd like to try them out. So this first slide is talking about free learning. The Open University's always had a number of elements of free learning. So if you'd like to try a virtual microscope for yourself, we have an external website called virtualmicroscope.org, and you can just go to that and use it for free. My favorite thing on there is that you can look at NASA moon rock samples. So from every Apollo mission, we have real samples of moon rock that have been scanned, and you can look at them on the microscope. So that's a great freebie if you've got kids at home, it's quite fun. If you'd like to use our observatories, you can do that if you sign up for one of our free courses. So we have a free Open Learn Astronomy course, and as part of that, you can use these telescopes that are on Tenerife. So again, that's a nice freebie if you'd like to try that. Something we found over the last 6 months is we've had a huge number of inquiries from other universities about using our Open STEM Labs activities. So we've been working with our education partnerships people to try to offer some activities for licensed use. At the moment, we're not offering any remote experimentation because there's a challenge with us gaining access to keep things working for ourselves, let alone for anybody else. So we've just gone with on-screen activities. They're not in the engineering field, but in the area of biology, health science, chemistry. We have a few activities that we're offering for license. So if you have colleagues who'd be interested in that in your university, please feel free to contact us. And we've also been trying to share some information through the pandemic period, again, because we had lots of inquiries. So we created something we're calling a showcase page. And if you just went on Google, do Open STEM Labs showcase page, I think you'll find it. This has put some of our resources available for free that would normally be paid resources. So I don't suggest that you try it with any of your students, but if you'd like to try and log on for yourself, you just go to the website, create a username, and you can try, for example, the Fourier activity that I've just shown you. So if you'd like to try a bit of remote experimentation, you can do that. And we've also written a blog about our way of working that links to some of our academic publications. Again, you might like to take a look. Okay, well, I hope you've enjoyed this kind of review of our Open STEM Labs at the OU. I just wanted to finish with a few key points. So really, the Open Engineering Lab uses digital technology to provide practical learning at a distance. And I hope you've seen from what I've shown you that it's really well embedded in our engineering curriculum, and it allows our students to build up their skills progressively and supports their employability. It also contributes to the professional accreditation of our engineering courses. And so we're very proud of the way that we're able to take some of that practical learning online and have it recognised as a value by professional bodies. And the Open Engineering Lab has also allowed us to continue our practical learning through the COVID-19 pandemic. We've actually had increased usage in 2020. So with that, I'll finish. I hope you've enjoyed my talk, and please try our free resources for yourself. Hope to see you again. Thank you.
Thank you, Helen. That was fantastic. Thank you. Really interesting. Amazing just how much can be done locally, as remotely. Actually, amazing how much can be done remotely. So we've got lots of questions for you here. First, the most popular one that's come in, been voted up, is how can a student receive support from staff whilst performing a remote practical activity? Is that ever in real time as well?
Okay, so good question. So we try to design the experiments that they can be done without live support. Obviously, our students are working at any time of the day and night because they're often working in a day job as well. So we have tried to design them so that they can do them without the support, but they can put messages on a forum. And what we find is that actually students often support each other. So they might find another student on a forum at midnight if they get stuck. But if not, we have staff checking the forums through the day and they'll help to fix problems. We do have a project planned to try and do live support. So that would be that they'd be on a timetable slot and they could press a button and ask for help if they get stuck. But we haven't got it there yet, but we'd like to do it in the future.
Great. Okay, thank you. And are any of your experiments more open-ended, allowing investigation, or are they all tightly bound to fixed instructions?
Yeah, so that's a tricky one, isn't it? And it sort of fits with the first one that, you know, if you can't give people support, you have to be a little bit careful. We do try to make them open-ended as we can. One of the things we try and do is build in ways to go wrong. So we sort of have dead ends that students can go down to kind of encourage them to try different approaches. Some of the electronics ones, we have lots of different options that they can go through. I think I'd say we go as far as we can, but we do recognise it's not quite the same as having physical kit in front of you where you really could, you know, be completely open-ended.
Good. There's some movement in terms of voting actually. So people are interested in the platforms. So what platforms are you using for your remote online experiments?
So the delivery is done through our Moodle virtual learning environment. So that's the sort of what the student sees at the front end. At the back end, we have a number of different ways of working. So I talked about on-screen experiments. So those might be developed using, say, HTML5, you know, the kind of one of the web formats. The real-time remote experiments, we've developed our own back end based on Java that allows us to have this very high response rate, low latency interaction. So it's a bit of a mixture, and because we have different teams working in different areas, we have a range of different technologies, but essentially it's delivered through the Moodle environment. Hopefully that answers the question.
Okay. I mean, if people did want to find out more about that, Helen, how can they find out more about that?
I put some web links in the presentation. I believe the presentations are going to be available afterwards. So if they went to the one that describes the website, they could have more of a look there. Or people are welcome to contact me and I'll send them more information. That would be fine. Yeah.
Right. Okay. So the next one, so drifting between academia and the workplace. So can this deliver practical skills for work?
So up until now, we've been focused on our own students. We also have some citizen science. So we've delivered some of our activities. I think I mentioned in the presentation about the telescope. So that's, you know, home users can use for free. And we have some citizen science projects with people contributing to bigger science projects. We've talked about work because we think there's something really interesting there. And we think, you know, we do offer foundation degrees, top-up degrees, people who are working. And we can see that there is a crossover with the kind of skills that they would want for professional development. So that's something we're interested in, but haven't done so much up to now. We are trying to think a bit more about how we're delivering skills as part of this. I think when we started developing labs, it was more about developing scientific and engineering learning outcomes. But what we've realized is actually part of it is this skills development, hands-on skills, data collection skills, you know, error tracking skills. And those are all things that would be great for professional development. So we're kind of trying to do a combination of the two and thinking how could we deliver this for work. And particularly we've had interest from developing countries for that. So colleagues in India and Africa. And we have a project called OpenSTEM Africa, which is training school teachers to deliver science school experiments. So I think, yeah, definitely there's something to be done there. We haven't done as much as we'd like to.
Okay. Next one, impact of COVID. So the OU has always been a distant learning based environment. How much of the Open STEM lab has been put in place because of COVID?
So I think the kind of question partially answers itself. Yeah, we've been doing the Open STEM lab for about 10 years in total. So it was all done in advance of COVID. We had our own reason to do it, the distance learning reason. I think when COVID hit, we were surprised how well we survived that COVID problem. You know, any activity, I think I said in the presentation, any activity that was online could stay online. And because we had the self-checks, we could be testing equipment during the COVID without anyone going onto the campus. So it did allow us to keep the activities going. I think what we've seen, and we've talked to lots of other universities in this time, because lots of people came and asked us how we did our projects. I think having had that time to develop really gave us, you know, a big head start over others. And what we've seen is that to do it quickly is really challenging. So some people have done a brilliant job getting stuff online, you know, in time to use with their students for this academic year since the COVID lockdown. We had the luxury of time to be ready already. It's caused us some issues with setting out equipment. We have some experiments that need multiple people to set them up. And obviously with the social distancing, we have issues with that sometimes. But yeah, no, we were up and running before. We did introduce one activity during COVID. So we had one that was almost ready and we managed to finish it off and get it live in April. But in general, they were activities that were already up and running.
Okay, yeah. Okay. I mean, did you see an uptake of interest there,
well, we did, yeah. Huge amount. Yeah. I mean, from external universities over the summer, we were just had a huge number of emails, people asking us what we were doing and could we help them. And as I said in the presentation, we have got some ways that we can help others. But in terms of individual users registering for a free, yeah, we had something like a 60% increase in number of users over the COVID year. So yeah, lots of interest.
Right. Okay, so the OU has always been a distant learning based environment. How much of the Open STEM Lab has been put in place because of COVID?
Did we do that one?
We've done that one. Sorry, my apologies.
I think it's the voting, isn't it?
Yeah, there's dynamic voting going on, which is
I think it moved it up.
Sorry. How do you integrate peer support, peer learning, or group learning within the student cohort?
Yeah, interesting. So the activities I've shown today are mostly individual ones. So the student is logging on and doing the experiment on their own. But we're keen to get group working in. We find group working quite challenging with students who are working in a distance learning environment. Obviously our students get together in residential schools, so they do some face-to-face group learning. But we're trying to build in some group learning into our activities. I could give you maybe one example from physics that we have astronautic students looking at a Mars rover mission where they're trying to look for water on Mars, and we have a remote rover that they can control in a kind of artificial Mars environment. But they do that one as a team and they log on together as a team to design the activities for that day, and then they send the rover off to do the work, and then the next day they get together and they look at the findings that they found overnight. And that activity is very much designed as a group activity where the students have to work as a team, they have to share resources and join together on a kind of a Teams meeting like this. But we found that for big groups, that's quite challenging. So works well for small groups. For larger groups, it's something I think we're still working at and we'd like to do more of.
Okay, interesting. So another one here in terms of how you've gone about doing it. So are simulated environments off the shelf or are they homemade? So like the microscope virtual environment. Yeah.
So most of our virtual environments are designed and built in-house. So we have a team of software developers and user interface designers that design those. I think generally the point has been they haven't found something ideal off the shelf. So they've always wanted something. We're a little bit ahead of the curve, so we've always been sort of pushing the boundaries, and there weren't tools available at the time we developed. The remote microscope, sorry, the virtual microscope had some external funding, and that's why that one's available for free as an open source project. So that was the history of the development of that one. But yeah, it was all developed in-house.
Okay, another one about you. Well, equipment checks here. So how do your automatic equipment checks work? And yeah. Okay,
I can. Yeah, I can give you a kind of high level description. I think I'd need one of my colleagues to give you all the detail. But essentially, we try to test that the equipment is working correctly between every student use. So if a student books a session, they usually book a 50-minute slot. And then the 10 minutes before the next student uses, we do an automated self-check. So if you think of maybe the pressure vessel that I showed in the presentation, in between the two slots, we have an automated system that follows the steps the student would do to increase the pressure. It measures the pressure at every step. It checks that it's within bounds of what a student should expect to get. If it isn't within bounds, it sends an email to someone that takes itself offline. And if we've got 8 pressure vessels online, it'll just, for the next student, try and find another one to allocate to the student. So it really is quite sophisticated. And in the middle of the night, every night, we do a kind of clean down where we sort of try and get all the temporary files off and restart everything. So it's quite sophisticated.
Yeah. Okay. Great. So you've created all these new things. You've developed all this technology, which is fabulous. So another question here is, does the OU have IP for these experiments online? So talk to us a bit about the IP side of things.
Yeah, well, we do retain IP for the experiments. We use them with our students internally, and we're working towards starting to use them with people externally. I think we're treading a little bit of a line because, you know, the OU's mission is to be open to everyone. So we do want to make sure that some things are available for free. We don't want to make it purely a commercial activity. So we have a kind of balance, and we have some activities that are for free and some that are going through a more commercial route. But those on the commercial route, yeah, we have a licensing in place that we can allow others to use, but we retain the IP to them.
Okay, good stuff. Yeah, and again, back so drifting between academia and the workplace. So does this replace the work? Does this replace work experience?
Yeah, I don't think we're saying it would replace work experience, but certainly for our distance learning students, it can be really, really hard for them to get work experience. You know, often work experience is available to students. They have to take, you know, a summer block or an extended holiday block. And if our vast majority of engineering students at the OU are working full time, either in an engineering environment or elsewhere, so it's really hard for them to benefit from the work experience opportunities. So I think it can be a little stepping stone towards getting some practical skills, you know, helping them to gain confidence with using physical equipment, engaging with engineering equipment, and then hopefully that's a stepping stone towards work experience. But we don't see it as a replacement, but certainly it can help to improve employability, help to build up people's confidence with practical engineering.
Very good. Yeah, great. So one other question for me: how does it, what you've done, how does it compare to what other organisations throughout the world are doing? Are other places doing similar things to this?
There are lots of people doing similar things. We think we're unusual at the scale that we've done it, over right across our faculty, and it's really well embedded in our curriculum. There are a couple of universities in the US that have done quite a lot. There are lots of individual examples. So within the UK, there are universities, many universities will have maybe a small number of experiments just in one subject. But I think the scale we've done it at probably is unique in the world.
Okay, and I mean, is this open to anyone in the world as well? Is that right?
The platform that it sits on.
The courses and things that you offer.
Yeah, so OU degrees, engineering degrees are primarily aimed at UK students, but you can study them overseas. Our teaching model, we have tutors, and so we don't have tutors everywhere. But yes, you could study it from elsewhere. But then the open activities are available to anyone. Yeah.
You could be doing these experiments. You'd be controlling these experiments from the other side of the world.
Yeah, anywhere in the world. Yeah.
Fabulous. Okay, and I think we just one final question that's just come in. So your introduction touched on the take-home kits that used to be offered. Does the OU still provide this at all? They still provide this as well?
So from my understanding, they pretty much stopped all the home experiment kits some time ago. However, in this COVID year, I mentioned that our students still do face-to-face residential schools, and we had to postpone all our residential schools this summer. Like other universities, we weren't able to offer them. And then we've had to take a decision that we will also postpone them again next summer, and we'll be offering a home-based provision for students next year. And that home-based provision will be based around home experiment kits. So it's sort of interesting that we've gone a little bit around full circle, but that's to meet the need that our remote experiments can give them part of the skill set, but we feel they still need some hands-on skills. So home experiment kits will give them that hands-on skill set. So interestingly, 6 months ago, I just said we don't offer kits anymore, but actually we will have them again temporarily next year.
Great, yeah, brilliant. Okay, Helen, just the final question then, just to close out. Can you just tell us what's next then? What's the future hold in this space then for Open Labs?
Well, we're always looking to develop new activities and new experiments. We are embedding it further and further through our curriculum. We started at level 1 and we're working up to the higher levels, and we don't yet have any in postgraduate in engineering. Perhaps the most exciting thing we have at the moment, we've bought 4 wind tunnels, and our mechanical engineering students in 2nd and 3rd level will be able to sit at home and control a wind tunnel to analyse the flow around different sections starting next year. So that's really exciting.
Helen, thank you so much. That was absolutely brilliant. Absolutely fascinating. We're now going to close for a short break. So we'll be back at 10:25, where we'll hear from Dr. Freeha Asmat, who will discuss degree apprenticeships. So I look forward to speaking to you all then. Thank you.
Thanks, Chris.
Hi, my name's Stephanie Baxter. I'm the IET's Education Skills and Innovation Lead. Thanks everyone for joining today's conference on transforming higher education. Obviously, due to the implications of COVID, the whole world has had to rapidly change, with industry also having the extra challenge of achieving the government's target of net zero by 2050. Clearly, the current pandemic has gone some way to accelerate this change, with many workforces now needing to operate digitally. To this end, we've surveyed over 1,000 engineering employers to find out how prepared they are in reaching net zero and the skills they need to achieve this. So without further ado, here's a quick snapshot of what they had to say. As we can see from the first slide, engineering is seen as the area in which most organisations report a skills gap, with over half saying so. This is a major problem as we move forward and rebuild the economy, as these skills gaps will need to be filled. Our survey also shows that 2/3 of employers think current staff will need more skills and knowledge than they currently possess. Only 1/4 of employees are adequately prepared. Here's a breakdown of the skills companies say they need to deliver their sustainability strategy. As you can see, innovation, management, and agility are by far the most important skills that companies think they will require. We can see from this slide that there is a split in how organisations want to recruit these skills, bearing in mind that some of these have selected more than one way. Although 38% of employers said they would hire new employees who already have these skills, 60% said they would upskill or retrain their existing workforce. Interestingly, 1 in 3 employees would recruit graduates or apprentices and teach the skills they require. Obviously, though, not every organisation will have the capacity to do this, highlighting the needs for industry and academia to work together to deliver training. Only 3% said they would do nothing, showing that employers are very keen to build up their skills for sustainability across the board. However, on the downside, there are many reasons why organisations are not able to address their skills gaps. Almost half are under pressure to reduce costs, which could be exacerbated by the current pandemic. 1 in 3 employers say that competition in the market for skills is the biggest barrier to addressing their skills gaps, which could be addressed if more of these were taught at degree or apprenticeship level. 1 in 3 also say that employers must be open-minded to new areas of growth and be able to change. And over 1/4 say that their business is not driving the reskilling agenda. This slide shows the perceptions of new entrants into the engineering profession. 57% of organisations think that university graduates do not understand the realities of working in industry. This is in contrast with 25% of technicians and 38% of apprentices. 43% of organisations agree that university graduates don't have the required skills for engineering, which is much greater than for technicians and apprentices. This slide shows where organisations are finding difficulties in recruiting. Almost half report that applicants lack the necessary technical skills, with 37% saying that applicants do not have sufficient work experience. 1/4 also say that applicants might not have enough soft skills, such as interpersonal skills and team working. And 1 in 5 applicants don't seem to be attracted by the conditions of the workplace or terms of business, including pay. When looking a bit more closely at the lack of technical skills, it's the lack of specialist skills or knowledge that seems to be the main problem. 1 in 3 of employers also said that solving complex problems or requiring a solution specific to a situation was also a skill that recruits generally lack. Many organisations are saying that they need more digital and digital specific skills, which is going to be even more important for the future. So I also mentioned that there are soft skills that employers say they lack. This includes team working, leadership and management skills in particular. These skills are important to every organisation, not just those in engineering. In some of the case studies you will have listened to today, we have and will see examples of how students can be taught these skills also while learning digitally. In order to tackle these issues, these are ways in which large and small employers are already engaging with the UK education system to be able to provide some more skills that employers are looking for. Understandably, this can be much easier for large companies who may already have the structures and resources available to them to engage with students and provide work experience opportunities and apprenticeship places. However, it's also really important that SMEs engage with students as they can show them how supply chains work and innovative ways of working. It also may encourage people to start their own businesses and develop entrepreneurship skills. Many organisations we surveyed identified key priorities for the UK education system as seen here. These are ways in which our respondents suggested would be the best way forward to ensure that students gain the skills they'll need for the future. More opportunities for work experience is the most favoured option, with 60% of employers saying so. Almost half of respondents suggest there should be more involvement of industry in the education system, with 45% saying there should be key targets for basic skills. 40% also said that project management experience would be really useful, and this can be delivered through coursework or managing a specific task. 38% of employers have said there should be wider provision of vocational courses, and the same number said that careers advice should be improved. So to finish up, what can we do as a profession to improve engineering skills? Well, we recommend that industry should work closely with academia to provide the practical and technical skills that individuals will need for the future. It might be that universities need to refocus to prepare students for anticipated growth areas such as digital and sustainability. Government should also ensure university funding is protected for these areas. We also need to work together to help build up the skills lost due to COVID, and also need to educate potential students about the value of studying engineering and different entry points into the profession. Lastly, just to mention that the IIT is focusing on 2 main growth areas over the coming years: sustainable planets and digital futures. We'd be delighted if you can get involved if you can, so please do get in touch. Thank you so much for listening, and do let me know if you have any further questions or want further information on this.
Our next presenter is Dr. Freeha Asmat from the University of Warwick, who will be providing a lecture on her experiences of designing a degree apprenticeship in engineering. Freeha will also discuss with us how to bridge the gap between academia and industry through degree apprenticeships. Please remember to ask your questions on Slido using the hashtag IET Digital Skills and vote up your favourite questions. I'll be asking several of them directly to Freeha at the end of the presentation. Thank you. Over to Freeha.
Good morning, everyone. Thanks for joining my session. I'm Dr. Freeha Asmat, Senior Teaching Fellow and Course Director for Digital Technology Solutions Degree Apprenticeship at Warwick Manufacturing Group, University of Warwick. Today, I'll be talking with you how degree apprenticeships are bridging the gap between industry and academia and trying to close the skills gap in UK. The agenda of my presentation is to talk about increasing demand of digital skills and how we can address that increasing demand using degree apprenticeships. Then I'll talk about the design of digital technology solutions degree apprenticeship at University of Warwick. I'll be going briefly through the curriculum and the way we have defined our business academia collaboration framework. And in the end, I'll be covering the impact of this course as well. So as we all know, fourth industrial revolution is happening, and it is changing the way the businesses, processes, supply chain, as well as the way the products are designed, fabricated, and used in many businesses. One of the survey done by Information Technology and Innovation Foundation found that actually manufacturing organizations can get 50% reduction in time to market for the products, and also the cost for quality and reduction in maintenance costs for many products can be occurred by using digital tools. So it is evident that the need for digital skills is increasing, and it's required in all companies and sectors of all sizes. On the other hand, the recent survey done by IET Skills in Demand, it found that 60% of the employers in engineering and technology companies in UK are struggling to find the people with the right skills. The survey was done across 700 employers in UK, and among that, 60% have reported that the biggest barrier to achieve business objective is to recruit the people with right skills. Also, 81% of the employers actually agree that businesses have responsibility to invest more in education and training so that the transition from education to workplace is much smooth. A similar kind of survey is done by Tata Consultancy Services, and they found that UK is losing £63 billion a year because the companies are struggling to find the people with the right digital skills. And there are 4 recommendations given by Tata Consultancy Services. And among that 4 recommendations, 2 are directly talking about apprenticeships. Companies need to invest more in apprenticeships and need to strengthen their relationship with education providers so that they can get the workforce in the right domain which they feel like. Now, those of you are wondering what is degree apprenticeship and how it is addressing the skills gap. So I'll briefly cover that basically degree apprenticeship is a job with education for a student. The curriculum defined for degree apprenticeship is driven by employer, and also it meets the national benchmarks like IET, Engineering Council benchmarks, but it's also employer driven, so it is meeting the needs of industry. On top of that, students is not expected to pay any tuition fee. They get the degree, they get their education, they get the training at the same time. So it's best of both worlds for student. But we need to see what's in it for universities and businesses, because we are the people, the university and businesses, who actually have to liaise and bridge the gap to offer a successful degree apprenticeship program. So from the business's point of view, businesses can use the degree apprenticeship to pay their levy, upskill their existing employees. And also, degree apprenticeship is a pathway where employers can play a key role for designing the curriculum and assessments as well, so that they can maintain a relevance with innovation and research. On the other hand, there are challenges for businesses. They have to invest their specific time and dedicated staff so that they can build more relationship which is stronger with academia. From university point of view, if we see, for a lot of universities, they have to conform to government policy by offering apprenticeship, but also apprenticeship offers the way the university can diversify their offerings of the full-time and the part-time programs. Actually, degree apprenticeship opens the way to offer the programs to traditional and non-traditional students as well. So universities have to work more on the challenging side by actually thinking about individual learning plans of the students that can help non-traditional students to also make the same pace as like full-time students. Apart from that, degree apprenticeship serves as a very good method by which more stronger relations with different businesses can be created, and these relations are long-term. Like for us at Warwick Manufacturing Group, we have a lot of industry partners working with us on board, and we have long-time relationship established from them because we are offering the services since long time using business academia collaboration framework. So there are challenges on both ends from university and businesses side, but in crux, university and businesses are closing this gap by using apprenticeships as a way forward. Now at Warwick Manufacturing Group, we offer apprenticeships in several areas. We offer apprenticeships in the areas of health, manufacturing, management, and digital technologies. The one which I'm going to talk with you about is Digital and Technology Solutions 4-year degree program in the areas of software engineering, data analysis, and network engineering. So basically, this 4-year degree program allows apprentices to get the right skills to be working in one of the key roles, which has been very important in the era of COVID pandemic. For instance, I'm connected to you via Zoom software. So if you need software engineers, we are actually liaising with each other and communicating with each other via internet. So network engineers are required. Similarly, data analytics is becoming the key for many businesses at this point. So we developed this degree by working closely with our partners, and we found that these key roles are required in companies of all sizes and companies of all nature. The way we designed this degree program is started with the conception of internal skills review survey with Jaguar Land Rover in September 2017, where Jaguar Land Rover found that the people with the digital skills are required in the company. Although it's a manufacturing company, but even manufacturing companies are going towards industrial digital transformation. So that was the key for starting this program. The initial requirements were taken from Jaguar Land Rover on board, and we started designing the curriculum. But we have designed this curriculum in 3 stages. We took the initial requirements, and then we designed the modules which were taken back to company, and their feedback was taken on board. Further on, once the feedback was strengthened and it was endorsed, then we actually changed the delivery according to our employer as well. So we went through 3 phases around like in a 1.5 year time to deliver our curriculum, but it is cutting edge, it's meeting the employer needs, and it also gives us a foundation to take any other industry partner on board. So basically around June 2019, another industry partner joined us on board, and we customized our curriculum according to their needs. As we did a lot of hard work while setting the foundations right, so it was quite easy for us to tailor the curriculum according to another employer. And finally, in September 2019, we welcomed a cohort of 80 students, which are working now in the 3 key areas, which I mentioned earlier, in the businesses and making an impact. I'll be sharing that impact with you in a bit. So the way that curriculum is designed is not about only that we follow with employer needs. We also cater the national benchmarks while designing the curriculum. Firstly, we follow with Institute for Apprenticeship and Technical Education Standard, which is a DTS standard, to ensure that our apprentices in the year 1, year 2 get the right skills in the areas of programming, databases, cybersecurity, business information systems, and project management. And then further, the apprentices will be split into 3 key roles, which is software engineers, as data analysts, or as a network engineers. In year 3 or 4, students will develop further specific skills according to the key role they're working in the company. And from year 1 till year 4, we let students do not only concentrate on knowledge, but also the portfolio of skills and behavior, because that's a key thing which actually differentiates an apprenticeship from a full-time education. We are talking about skills and behavior which are being, developed in a 4-year time span. We also conform our curriculum along with IET AHAP pillars, so that 5 areas of competence and commitment is also followed. And in the end, we expect our graduates to get incorporated engineer status. We also follow with quality assurance benchmarks. So the main key is that degree apprenticeship is the way in which you act and work closely with employers. Also, the curriculum is rigorous, that it's meeting the national benchmarks. And on the other hand, it also closes the skills gap, which is the cutting edge, by offering the roles in the key 3 areas. I would also like to highlight that while designing the curriculum, we wanted industrial rigor, and we also wanted to close the mainstream digital skills gap by offering the technologies and covering the concepts like Internet of Things, cloud computing, and cybersecurity, data analytics, agile project management in our curriculum. These all concepts are covered, some at the broader level and some in depth in our modules. And when we are actually covering this curriculum, we ask our students to actually apply their workplace using work-based projects. So there's a lot of work-based projects in several modules, and we have developed the industry academia collaboration framework by actually defining a specific role in the business, which is a subject matter expert role, and that gives counseling to our students about the work-based project. The subject expert role, I'll talk briefly here because it's very important for any industry academia collaboration. Basically, these are the people who are working on the company side, and they are working with our WMG lecturers to support the work-based project, work-based assessments, or even give guest lecturers. So far, like, in the COVID-19 pandemic, although it seems like, the collaboration seems to be going through very difficult phases, but still our subject experts supported our students by giving them guest lecturers in the cutting edge areas which are appropriate for the business. Also, our subject experts define and give us work-based projects, work-based data sets for our apprentices to work on. So it's really builds a linkage by which students can apply their theoretical knowledge back into the workplace, and they can see what we are teaching them in the class is applied in the real world scenario. There's also a thing which I like to highlight about business academia collaboration when they work together. It's not about only the module content design assessment. Also, we have defined a role which is apprenticeship tutor role, and that gives pastoral support to students during their journey in apprenticeship. So basically, apprenticeship tutor is a role that bridge the gap between the academic tutors and line managers. They meet apprentices 4 times in a year, and they ensure that apprentices are not only gaining the knowledge, but also they are getting the skills and behavior at the same time. And these are the people who actually spot individual learning plans for a student. If they are lacking in one of the skills, basically they come to us and they come to line managers, and then we define individual learning plans for our student. So to make a successful degree program, it's very important that academia and industry comes close from the point of view of academic quality, monitoring, as well as design and delivery. And that's what we are trying to do. And we are very happy to share that program is working successfully. And I want to share some of the comments given by our DTS Year 2 students, how they are making an impact in the company. And basically, these students have just done their first year of study, and we are happy that they are using the constructs which they have studied in year 1 into the workplace. Like some of the students have said that the knowledge they have gained through the course is often the building block for doing any task which is given at workplace. Also, one of the students has actually optimized the way vehicular communication networks work at the company by using their programming knowledge. So in Crux, the academia industry collaboration is working fine. And I advise that once we define such linkage, we give very special care to the delivery design as well as the linkage between 2 entities. In summary, I would like to say that apprenticeship is the key to strengthen and close the academia and industry gap. And our DTS degree apprenticeship has been designed with our industry partners, but we need to support our students by company cohort managers, apprenticeship tutors, and wider degree apprenticeship team. In the end, I'd like to acknowledge some of the key people who are playing a very active role in the delivery of the program and also played a very key role in the design of the program. So they are listed here. And that's all from my end. Thank you very much for listening to me, and over to you for question answers. Thanks.
Thank you, Freya. That's fascinating and amazing how many different options there are now compared to when I did my degree. I must say, it's really, really fascinating how things have moved on. So we've got lots of questions for you. So we'll start with this one. What is the most important thing to remember when designing a degree apprenticeship?
Thank you. Thanks very much, Chris. And firstly, I will agree with you that I didn't have much options during my undergraduation to go through, different routes. We had only full-time degree. So I think degree apprenticeship has got a lot of benefits for the students now. Anyway, coming to your question, while designing degree apprenticeship, one of the most important thing is adhering to degree apprenticeship standards, which has been mandated by Institute for Apprenticeship and Technical Education. So within these standards, there's already, list of knowledge, skills, and behavior, which are recommended by top tier companies in UK. So they have already, come up with the knowledge they're expecting in their companies for students to have, the skills, the behaviors. So that was the most important thing, that, you keep that like a holy book to you and then follow it. And then on top of that, you follow employer requirements. But what I would like to highlight is that saying knowledge, skills, and behavior is quite easy thing, but in full-time degree programs, when we design, we only talk about knowledge, but we don't see and we don't create opportunities for students to get actually skills and behavior as well. So that's pretty much a big challenge, that how you can actually create that opportunities with employers, and they're called work-based learning opportunities, where they actually can apply their knowledge and get the skills, and also, follow a specific behavior, which is also then recorded in a portfolio. So that is one of the most important thing, and also making sure that it is meeting the needs for each student is quite a challenging job. Thank you.
Right. All right. Thank you. Yeah. So there's another one here. So current data suggests that degree apprentices are from wider participation backgrounds at a lower rate than traditional degrees. What could or should be done?
All right, I completely agree with the comment, and I think the data is depicting what even is happening in our university as well, that there are more people who are coming from the traditional background. And I think there are a few reasons behind it, because when it comes to widening participation, basically we have to make flexible options for entry points in a degree as well. And I think the entry points normally we are used to are particularly A levels, not maybe the BTech courses. And if they are BTech, then they didn't have that specific grades, which we are looking maybe at a Russell Group University. So we are currently working on bridging programs so that we can actually encourage more people from widening participation to come in, which are actually coming maybe from colleges or from a technical background. And then we provide them some bridging programs so that they can actually then come to degree apprenticeship. So for instance, if somebody has not done maths and they have not actually done maths in GCSE, or somebody has not done computing at all, so basically a bridging course can upskill them to a level they can start level 4 degree apprenticeship. And I think that sort of bridging program is something, a way forward for many universities if you would like to wish to increase widening participation, because I think the main gap is that entry point needs to be uplifted. And we really need to see how we can have more people who have got actually talent, but they are not able to enter due to their A-level grades or maybe their previous, experiences. So we give them prior learning experiences, or even, some credit to get bridging programs. So that's pretty much one of the main, I think, way forward, which I see to increase the ratio of WP.
Okay, thank you. So one question now around the regulator. So with Ofsted due to take Oversight's full degree apprenticeship provision in April next year, what are your thoughts about this and how it will affect how you deliver your program?
So it's again one of the another added challenge now for degree apprenticeship, because with Ofsted obviously we'll have to come up with more regulations which are adhering to their standards. But what I would say is that if we have collaboration between employer and university properly done, and that's recorded during monitoring phase, during delivery phase, that pretty much, feeds into what even Ofsted requires as well. Similarly, the grades and the widening participation requirements, then how you meet knowledge, skills, and behavior framework, that also feeds in that it's not a traditional degree which Ofsted is actually checking, it's checking what we are bringing on top of that. So it is challenging, but what we are doing on top of that from our end is that we have now start making record of even, our old steps. We are making sure we are, doing to make sure degree apprenticeship is successful. For instance, if students are not getting exposure to a specific, you can say, concept for a particular module, and there are a specific set of students, we create individual learning plans for them, and then that's recorded on top of that. So we are trying to go to the student level as well, and on top of that, on the management level as well, that there is collaboration and that's recorded too. So that's a way forward. Yeah, thank you.
Okay, thank you. So, so in terms of progression, actually, from the degree apprenticeship, so another question here, do you see progression from degree apprenticeships to higher degrees at the same rate as those from traditional degree backgrounds?
Exactly. I completely see that, and very, you can say well-defined question specifically for digital and technology solutions, because for DTS specifically, we have got level 7 apprenticeship standard already with us. Level 7 apprenticeship standard means the master's level for digital technology solutions. And there are actually several level 7 apprenticeship standards for other undergraduate degree programs. So I completely envision, and actually we are working on, creating a version of that. But even for other universities, I completely envision that there is a progression from level 6 to level 7, even for digital technology solutions. And there is a way, like once you get honors degree, you can actually start any other master's program, which is part-time and accredited by other university. But what I can see from IFA currently is that there is more movement towards level 7 apprenticeship standard for some of the courses, specifically including this computing course, because there's a need. And we are seeing that our DTS graduates will actually get into their master's qualifications in the next few years' time. So there's a possibility, and it's, I think, going to be very you can say famous option for many students, because they're looking into this question. Even when they started, they ask us this question, what I'm going to go, do after 4 years. And we were telling them there are more options for you in a few years' time.
Okay. Good. And I mean, in terms of just linking it back to the linking it to professional institutions and the qualifications. So the question here around are these degrees accredited by the Engineering Council and the Institution of Engineering and Technology? Do they count towards being an incorporated engineer or a chartered engineer?
Exactly, they do. Thank you very much, Chris. So the answer is yes, they do. Currently, we have applied engineering program at Warwick, which got incorporated engineer status. And moving forward for digital technology solutions, we are aiming to get accreditation from 2 bodies, one from Institute for Engineering and Technology, IET, and the other from BCS. And I have been, in quite a close contact with BCS, and we are finding out the ways that they can actually get even partial CEng when DTS graduates, go. So the way is that when we design the degree, we ensure that engineering council framework, also the codes for competencies and commitment from IET, they are taken into account while curriculum designing, and they are being liaised and agreed with employer. So actually you don't need to do any further work when it comes to 4-year time and people are going to graduate. You have been making sure they have got that experience in 4-year time, and this is what we are trying. So from IET perspective, we are envisioning the IEng, and BCS actually in the initial conversations have told us there's a possibility to even go for partial CEng. So that thing applies to all DTS standards, I would say countrywide. They are completely accredited. And that's why I think that doing degree apprenticeship is best for a student, because you can get an accredited full-time degree, you can get a full-time job, and you can get experience as well. It's just the hard work which students has to put in, but it brings best of all things together.
Yeah. Okay. Yeah. I mean, just building on that, and so another question here around what do you think what are the benefits of the degree apprenticeship compared with going to university?
Okay. Thank you. Thanks, Chris. I think pretty much that's similar kind of thing which I just commented, that if you go to university, mostly you may get placement in industry after a year or maybe 2. And that's also maybe for your months, summer months, or for summer placements. So you lack industry experience. You're only getting academic education. You're not getting a chance to apply that. So the best thing you're getting from degree apprenticeship, you're applying your knowledge continuously at workplace. On top of that, then you are not paying for your tuition fee. So it's all paid by employer, which is again best, because it's not putting anything on your pocket. And then on top of that, you get pay as well. So you can get your early mortgage if you like. So you're getting pay, you're getting experience, and you're getting you have to pay no tuition fees for a student. If you think from the financial point of view is best, on top of that, I would say experience wise is quite good, because whatever we teach, they have to apply. If they're not able to apply, they come to us and they tell, what would be the implication of that, how we see that in the workplace. So this is a very novel thing, I think, that integrating real world experience with the knowledge.
Yeah. Okay. And then there's a sort of related question around, are the students attending, is it day release or block release, or is it a different attendance pattern? So quite a specific question around the attendance there.
Yeah, so currently for the program DTS I have mentioned to you, it's a block release, but at Warwick Manufacturing Group, we have different programs according to employer needs. There are some day release methods as well. We do according to employer specific. It's not generic that we just do block release. For our case, we chosen it, our employer agreed, but there are other courses as well we do day release. So both actually work, and it depends how an employer wants and, want to release their apprentices for a specific, class.
Okay. Okay, so yeah, just on the employer side then, there's a question around the different types of employers. So for SMEs, the sort of small and medium enterprises, what are the barriers for SMEs and startups to be doing these degree apprenticeships?
So from SME point of view, I mean, they are not able to, they don't have that much levy to spend towards, training. That's a barrier, but government is helping SMEs to have specific number of apprentices to be topped up, and some finances from SMEs and some from government, basically. That's a way forward. But on top of that, from SMEs point of view, then we do work closely with them as well if they want to go for sponsored degree. So there are degree apprenticeship possible, but somehow some SMEs will pick up sponsored case, or some will actually take help from government, and they do it together. I do agree that there are some challenges and limitations associated with participation of SMEs, and we don't have that much on the board, but we are trying to, give them more than short courses. If they like to wish and come send their employees for short courses, we are also helping them to upskill employees in that way.
Okay, and one around the sort of the flexibility of the different modules. So is there one curriculum, or do students from each company have different modules, different learning?
There is one curriculum following, as I said, Holy Bible, which is like Institute for Apprenticeship Standard. With employer-specific, variations, we have only may add few projects, which is again, liaise with employer, or some specific details. But all curriculum is generic, which is according to different employer needs. On top of that, we create work-based learning opportunities. So the work-based project is part of it. In future, we are actually introducing work-based learning modules, where they can actually just, apply their knowledge in a module and show us how they have done, a specific learning. So that sort of flexibility, which is work-based learning module, can actually bring a lot of freedom for employer. They can ask their students to maybe go on a training and do a specific course for their work, and then get credit for that as a part of our degree. So we are also now embedding that, but it's not like for each employer we have a different curriculum. The basics are same. Small variations are then liaised depending on how much it can be catered without influencing any sort of learning outcomes on the higher level. From the Institute for Apprenticeship Standard or IET or Engineering Council, is not impacted. We make such small variations because at the end we want our apprentices to get same accreditation from each employer. It should not be employer specific to that extent that one get IEng and the other couldn't attain for that. So we ensure that we need the basic benchmarks, and then on top of that we create some variations.
Okay, and then in terms of sort of life beyond the apprenticeship, the degree apprenticeship, and people's longer term career aspirations, there's a question here around, given that employers lead apprenticeship standards design, to what extent do degree apprenticeships set learners up for whole careers rather than just particular jobs?
All right, I think that's again a very good question, and we have faced sort of that during our discussions as well. When employer comes, they sometimes comes with very niche training needs, that I want my apprentice to learn this tool, this specific technique at this time. And at that time, I think it's the university role as an academic, entity to really mentor them as well, that what is academic level 4, level 5, and level 6. And we want our students to actually be, University of Warwick students as well, and make them prepare for the future as well. So we can actually entertain your training needs to maybe 80%, but 20% would be another academic, you can say rigor, which we add from our end. So during our conversations, we that's why it took us like 1.5 years to design this program, because we keep getting requirements and we keep working on it, that what's doable for student favor for the long run and what's only actually good for the short outcome. Because if you make student to learn a specific software for a company, they actually will not get the idea how to actually work with generic software. So the way we work is not like we pick only a specific software for a company to teach them. We pick our generic platforms. We teach them programming database generically. And then maybe one day is dedicated for company specific lectures so that they can also get company specific knowledge. Then the project can be company specific as well. But the way the teaching is done, it's more generic, because that's the main aim for a university education. So I think it's more about the collaboration and the time you are deciding and negotiating with your employer, that how much flexibility you can bring in and how much is possible considering academic needs. Yeah.
That's great. Thank you.
Yeah.
I think that's about all we've got time for. Dr. Freya Asmat from the University of Warwick, thank you so much for your time. Really fascinating, and all the best with degree apprenticeships going forwards.
Thank you very much, Chris. Thanks for your time and really, insightful questions. Thanks.
Okay, we're now going to take a short break and we'll be back at 11 o'clock to hear from the University of Middlesex discussing digital tools they've been using because of COVID-19. So speak to you all then. Our final presenters for today are Professor Mehmet Karamanoglu and Luke Bennett from the University of Middlesex, who will be discussing some of the digital tools they've been using to teach students because of COVID-19 restrictions. They will also discuss some of the practicalities and issues they've faced in implementing these at pace to match COVID need. Please remember to ask your questions on Slido using the hashtag IET Digital Skills and vote up your favourite questions. I'll be asking several of them directly to Mehmet and Luke at the end of the presentation. Thank you, and over to Mehmet and Luke.
This session is about the experience at Middlesex University in response to remote teaching tools that we had to resort to during the pandemic situations. And my name is Mehmet Karamanoglu. I'm the head of Department of Design Engineering and Mathematics at Middlesex University. And Luke Bennett, who is also associate lecturer, will be joining me in this presentation. Just to give you some introduction and context to this presentation. Middlesex is based in London. We have a single campus at Hendon, and we have typically around 22,000 students on campus when we're fully up and running. And in terms of the context, the presentation relates to our provision in engineering, and which is largely practice-based. And I'll then be going into sort of challenges that we faced at the point of the pandemic, and also what technologies we had to resort to that was available at the time, and what we have now put in place in terms of short-term and medium-term solutions to overcome these challenges. And we'll also play you some examples of, some clips of examples of how we were using these technologies. In terms of the way we're teaching and our curriculum is based, it is largely practice-based, and there are no mass lectures, quite unusual for engineering provision in the UK, or end of year examinations. So all of our teaching is based in the lab and as workshops, and we do also assessment to match with the ethos of the delivery, which is practice-based. That in that case, that the assessment is probably best done by project work, prototype building, that are appropriate to match with the learning style and the teaching strategies. We work in teaching in teams of staff, so we tend to run our sessions over 3-hour periods in workshops or labs that covers content as well as practical elements in one go. Most of the teaching material is available online, so students see that prior to coming to the sessions, and when they do come to the labs or the workshops, they're there to actually implement what they would have read. And we do a small amount of input, but it isn't a traditional way of working in terms of engineering teaching. They do come to the sessions to do practical work, and that's how they learn. And we've been using this approach since about 2010, and our programs are fully accredited by the provisional bodies that meet the competences expected by the Engineering Council for CEng registration. None of us foresaw this coming, I think, in the HE sector in terms of the pandemic. We typically had about 2 weeks before the end of the term that we were going to be disrupting teaching. And the only option for us was to transfer our delivery onto online. And we had about 2 weeks notice. I don't think none of us was, to be honest, was ready for this, but we did our best. And then we managed to use the tools available at the time to deliver the last 2 weeks of the teaching that was left to do. Most of the content was delivered through an online medium called Cultura Neuro, which is a bit like a Zoom that is now available widely. The advantage of that, this was already built into our VLE system, which was Moodle. So it didn't take too long to set this up, but it was not ideal. We needed to extend our deadlines, particularly in our sessions where, in our area where the teaching is largely practice-based, because there is no end of examinations, there's all practical assessment, which we now had to modify to match with what was practically possible. Many of the final year projects had to be finished off using simulated outcomes, using simulation modeling and verification and validation, which I think work quite well for most cases. So we don't believe that much of the students were disadvantaged in terms of the final outcome, but it was a pity that they wouldn't realize the end result as a physical object that they would normally do. Now, having had the teaching sort of finished off for the mostly undergraduate provision around April, then but postgraduate provision continued throughout the summer, because those are 12-month programs. And we use that period in the summer to test some of those digital solutions that we are now using on small cohorts, which is typically what the postgraduate programs are. And we've now embedded those into our mainstream teaching now that in the new academic year. But some of the shorter term solutions that we had to put in place is that we didn't expect that we'll be back on campus in the autumn term fully. So we needed access to specialist computers, and not all students will have sufficiently powerful computers at home or laptops. Then what we decided to do is to convert all our specialist computers in the labs, about 300 plus, to be able to be connected using remote access. And we use a client called Splashtop, which will be an example of this later on, how we manage giving access to students with high spec machines that can carry on and doing normal classes they would have there. Many of these specialist softwares that we're able to either allow students to download and install if they have got capable machines on their own machines. And there's a application called Apps Anywhere that virtualizes a lot of the software. And that was a project already in place, but it is now very much used by students across the board, not in my faculty, but across the university. Another new aspect to this was to look at how we could give access to quite expensive machines remotely connected for students, so that they could connect to these and make use of them and carry out experiments. And we'll give examples of this as well. This is, for example, of how we currently teach robotics in terms of teaching. That's a programming environment called ROS, Robot Operating Systems. We have a number of machines. You can see them in the background. They're labeled as A to J. Each student can remotely connect to a laptop or a computer that are attached to those mobile bases, and they can program them offline using a remote connection. In the room, there are also staff present while the students are at distance, and they can test their program to see what it will do, but they can see the visual results of what the robots are actually doing. And you can have multiple students on this at the same time, and part of us will be obstacle avoidance, avoiding other robots as well as the objects in the way. And that will be the kind of things that we are now doing that I think will probably have a longer lasting effect, that we will be able to allow students to connect remotely when everything is trying to get back to normal, or the new normal that we'll probably have. That there are some new ways of allowing access to equipment where there may be difficulties for students to join physically. The examples that we're going to talk about, I think I'm going to hand over to Duluk shortly, but we have 3 cases where we're going to be looking at what technologies we are now able to use to pass data from remote machines to physical machines, and then vice versa. So the first example, we'll be looking at the TCP scripting, and then we'll look in terms of how we can use remote access to physical equipment to program devices, something like programmable logical controllers. So this is something that we do on our automation and mechatronics programs. All students need to be able to program these devices. We'll also be looking in terms of what other software packages that were now available, and then we can join this, even from different vendors, to achieve a simulated validation that happens on part physical and part digital systems as one. And there's a lot of work going on in terms of digital twins, but this is for looking at undergraduate and postgraduate level work. I'm now going to hand over to Luke to take over these examples in turn.
Hi, I am Luke Bennett. I'm an associate lecturer at Middlesex University. This first example will demonstrate how we can pass live data streams from our industrial equipment based on campus at our university towards remote equipment based externally to campus, whether that being staff or students' machines. We have the ability to pass data between industrial devices residing on campus and devices external to our facilities with the use of a selection of communication protocols. To allow this capability, both computers must be connected to the same network, and this can be achieved with a VPN client. Now, in some circumstances, the transfer of data may only require the use of the TCP server client programs, but our method requires the extra integration of OPC clients to retrieve data from our host PLC on campus, along with providing data to our PLC residing externally to campus. As you can see within the tag table, we are transferring data from 16 digital IOs, along with 4 analog inputs and 2 analog outputs. You will also see me toggling the input states of the PLC within the top right of your screen, as well as the 4 analog inputs. The state changes can be seen within the tag table. Here we can see the 2 communication programs that are run on the host machine. Both are programmed within the LabVIEW environment. The OPC client takes data from the host PLC and passes it onwards to the TCP server. Again, you will see the repeat of the state toggle in the top right of your screen, and the response will be shown on both front panels of the LabVIEW programs. The TCP server broadcasts all data locally on a specific port. Here we have the 2 LabVIEW programs that are run on the remote computer external to campus, with the TCP client on the left of half of the screen and the OPC client on the right. We need to specify the IP address of the host computer along with the port that the TCP server was publishing within. This data is then passed on to the OPC client, to which it is then written to our remote PLC. Providing that we have specified its IP address. This time you may notice a small delay between me toggling the inputs to its response on the indicators. This latency will depend on how far the packets of data must travel to the remote host. This is the response to the data being written to the remote PLC. You may notice that the digital data is written to memory bits and the analog data is written to memory words. This is to allow the end user to interpret the data and make informed decisions within their PLC program. As you can see, this method of transferring data was particularly helpful to allow a group of postgraduate students to remotely complete their assessment during this past April. They were initially tasked to interrogate our cyber-physical factory and introduce a new conveyor line to export pallets of the factory to an industrial robot arm for for the aim of additional functionality. The COVID pandemic forced our students to revert to remote connection and virtual commissioning of the project instead. Although within this application I have demonstrated exporting data to and from PLCs, you are likely to be able to achieve similar methods with many different types of device. This second example will showcase how students will use a remote access client called Splashtop to access the machine, the computers residing on campus, to configure and take control over our industrial equipment, in this instance PLCs. Our solution to provide remote access to our specialist equipment within the labs is with the use of a remote desktop client called Splashtop. Splashtop allows our IT administrators to set defined privileges to each user based upon the program of study to which they are partaking within. As you can see, I have access to 155 open access machines, along with 2 sets of 12 machines between our specialist laboratories. If we go to open access computers, we can see that the machines with a circle surrounding them, they're machines with students already gained access to those particular machines. If I was to go and try gain access to one of our specialist machines, gain access by entering the password, and to open the webcam that's based upon the equipment that we wish to take control over. Okay, if I open up Siemens TIA portal. TIA portal is the environment to which we can configure and program PLCs, programmable logic controllers. And if I'm going to, I should open up a project that I created earlier. And perform the necessary steps to connect to the device. Okay, as soon as I change the CPU into run mode, our digital I/O will start to change values, and then I can switch the webcam to display the output of the actuators. So our digital I/O is changing, and we can see the output of our actuators, double acting pneumatic cylinders, all controlled by the PLC in the top left of the webcam image. click stop the CPU to stop the process from running, and our actuators are stopped oscillating. I can close TIA portal and the webcam and relinquish control of the laptop. This final example showcases two methods of how students can overcome the loss of physical interaction with equipment by the use of simulation methods. Here's some simulation software packages. During our undergraduate programs, our students were required to design and build mechatronic circuits based upon given design challenges. Usually when students are present on campus, they would have the ability to build such circuits using physical components as shown, whether the design challenge is pneumatic, electro-pneumatic or PLC controlled circuits. To continue to allow our students the necessary opportunities to continue with this method of study, we have needed to transfer to simulation, and our chosen software package for this purpose is Festo FluidSim. FluidSim is a world-leading circuit design program for both pneumatics and hydraulics. You can design circuits by using a selection of components, and based upon component selection and placement, different outputs can be achieved. Another software suite we are using is Siemens NXMCD in conjunction with Siemens PLC Sim Advanced. NX Mechatronics Concept Designer has easy to use modelling and simulation which allows you to quickly create and validate design concepts. It is packed full of libraries that allow you to introduce kinematic and dynamic properties onto base CAD models for rapid prototyping and development of mechatronic systems. NXMCD allows the convenience to virtual commission systems and ascertain responses before any requirement of a physical model. As mentioned in a previous case study, our postgraduate students had to change their assessment to use simulation after the arrival of the COVID pandemic. What you can see is the outcome of a very successful project with the use of NXMCD along with remote connection to a computer residing on our campus, and also the live data stream passed on from our cyber physical factory. Our students were able to validate how effective their solution was to the given assessment requirements.
Well, thank you, Luke. That was brilliant. Thank you much for those examples. And I think we'll wait for the audience to come back with some questions. But
thank you very much for your time. I look forward to answering some questions.
Thank you, Mehmet. Thank you, Luke. Absolutely fascinating stuff. We've got lots and lots of questions for you. So yeah, people are obviously really quite intrigued by this. So let's get straight into it. What was the advantage of remotely using the real robots for ROS activities over simulators, given that students could remotely access powerful PCs? So Mehmet, do you want to take that one?
Yeah, I mean, in terms of ROS operating systems and how we will use if the students were actually physically present, there are other features that you will see in terms of pathfinding and also to be able to get physical contact within the proximity of the robot itself. Now, in terms of the advantage of remotely using the real robots as opposed to simulation, you can see physically what the robot is actually achieving rather than a simulated world. So in a simulated world, you may not necessarily be aware of the surroundings in its true sense and to physically have it to operate. And there may be other things that are not part of the simulation or overlooked. So to be able to see how the system will actually respond physically, even though you're not there, but you can still see the response through video or webcams. That has an added advantage of giving confidence in terms of your learning and the achievements in terms of the learning outcomes.
Okay, thank you. So have you experienced problems with students not having sufficient internet speeds to make use of the remote technology?
Look, I mean, you deal with this on students on base.
Yeah.
Do you want to take this one?
I mean, we have had troubles with internet connectivity, but all of our lessons, we use Zoom and some other platforms. All the lessons are recorded in the cloud, so our students then we can replay we can offer the support to replay the recorded sessions online, so the students can then, if they feel like they've missed anything due to connectivity issues, they can then come back and review what they feel they've missed out during that period. Okay, we make sure that while we're having the lessons, we're going to make sure that our connectivity is over LAN, so we should our connectivity shouldn't drop at all, whether that's being from home or on campus. So if we can allow our connectivity to be on board at all times, then it will be recorded to the cloud, and the students can review that if they miss anything at a later date.
Okay, thank you. So there's a lot of vendor-specific software shown, Siemens, Festo, etc. Do the students get blinkered by these platforms? Are there open source alternatives?
Yeah, I mean, I can have a go at this. Yes, I mean, in the case studies we've shown that we've used quite specific applications from our industry partners. Now, they're strategic part of the curriculum, so that they're actually embedded into the curriculum, so they're not just for advertising. It is actually part of what we were built on the programs on. Do they get blinkered? Well, they certainly get familiar with the sort of the market dominant software, but there are some open source alternatives which they can use. I mean, for example, in terms of PCB or electronic circuit design, for example, they can certainly use Eagle, which is open source. But on the flip side, we do have Altium, which is more industry standard. They're given those alternatives in case they can't, post-graduation, they can't get access to the software, so you're able to use these alternatives. So we try and make them aware of all these alternatives, which are mostly open source, in case they need access to similar software that they're not able to get to, bespoke ones from our industry partners, which is paid software. We try and make them aware of the alternatives in case. But the reason why those case studies feature so many bespoke software from Festo, Siemens, that was the nature of the sort of setup we currently have.
Okay, thank you. And a question around cybersecurity. So people are obviously thinking about that. Have you any cybersecurity concerns with allowing students remote access to the operational technology equipment?
Yeah, I mean, that's a big concern, but particularly from the US's point of view. So everything we provide goes through quite serious checks, and then nothing is accessible unless you use a VPN to connect directly. So yes, we do recognize there's a threat, and I think there's no foolproof system, but you try and take measures that forces people for, even for Zoom calls, we only allow access to authenticated users when it comes to attending lessons, as well as connecting to physical hardware, and they'll have to go through a virtual private networks that we've set up.
Okay. And how much of this, have you still been able to engage with overseas students using this technology?
Yes, I mean, we had no issues with students connecting remotely, provided they have sufficient bandwidth in terms of internet access. Students do currently connect and use remote services from other countries.
Okay. And how much of this technology will you take forward post-COVID? Another question.
I think we're learning from this, and I think the biggest shock for us was that actually the implementation was so rapid, because we only had a couple of weeks of notice to switch from face-to-face to online teaching with no infrastructure that was ready to allow this change. But having now lived with it for several months, and now we're in the new term, new academic year, with mostly online provision intended, we've now put in place infrastructure that will allow us to deliver this successfully. But there are also areas that we'll want to retain in terms of enabling sort of broader access and a wider reach for people when they cannot perhaps access the physical resources, and we can then allow that to happen. We're also looking at, we have international campuses, for example, so students there can access equipment that are not available in those campuses. So there'll be lots of, I think, useful things come out of this pandemic that we grapple with. But I think there are some positives that I think everyone in lots of different universities will try and keep some of this learning that was imposed, but I think we will also benefit from it in the longer run. We will also look at developing different types of program provision. For example, blended learning will become perhaps the norm in the future, rather than everything is done face-to-face.
Okay. And how about the student and staff experiences? There, a question here: how are students and staff finding the experience? Let's talk a bit about that.
I think because we were not ready to make the jump, different people responded in different ways, and some staff are not as technically savvy as others. I mean, in my faculty, which are science and technology, for example, we tend to be a bit more tech aware, but there are other parts of the university where this becomes a bit of a challenge for staff. So, and the same thing applies to students. Some were more confident in the use of technologies, but what we do find is that we were concerned in terms of multiple platforms, in terms of whether we use Teams, whether we use Zoom, whether we use something called Cultura Neuro. We wanted to stick to one system so they're still familiar with it, but we have not seen any problems with students switching platform. It is more of an issue for staff that they get familiar with one platform and they prefer one against the other. Initially, we started with Cultura Neuro, but I think we're now converted to almost across the board with Zoom because of more reliability issues and also flexibility that it offers. Okay. But yeah, there's been a sort of learning curve at different pace by staff and less so by students.
So it's also different challenges. I mean, from a technical aspect, I think I'm an adept, but maybe also the different approach to how we teach. Well, we're used to face-to-face teaching. Now the different aspect is from a remote environment, so maybe through Zoom. It's just a different approach. So in my challenges, for instance, I'm having to get used to the approach and how the interaction between the students, and how I can get the best for the students going forward while we remain in this environment.
And if the student, if they engage in this way and they do the remote work, the remote experiments, do you count that as practical experience?
Yes. Yes.
Yep. Okay.
Yeah. It's never going to be the same in terms of having hands-on experience with the equipment, having that touch element. But we're trying to align, and each approach that we have going forward, even from these remote sessions, we're trying to bridge that gap, as you were, as close as we can. And there are still differences between being physically on campus and being remote, but the more we can do to bridge that gap, the better for the students' experience and their engagement going forward.
And if they need to ask for help, how do students ask for help if they need it?
Many avenues for help. They can contact us formally via email. They can raise their hand within the Zoom sessions or the Microsoft Teams sessions that we put on. They can also just open conversation like we were during the sessions, depending on the class size. I know that during my classes, I've set up a Telegram group chat. So very informal kind of forum chat conversations going on where students can raise their questions. They can also help each other out. So I'm part of the Zoom, the Telegram chat, but also if I take a little while to respond, the students can then help out each other. It's a collaboration effort. So that's another aspect where students can raise their concerns or questions in an informal environment, and that seems to help too.
Yeah, I mean, just to add that we're also getting into enabling, alongside the Zoom calls, for example, that is recorded. There's also some that I think we didn't, because most of us operate the Office 365. So Microsoft now made the whiteboard as a feature, which is a bit like the paddle that a lot of people use. They allow students to contribute online and offline to issues that was raised, that was similar to what Telegram is doing with that. So there are other alternatives in terms of engaging the interaction that which is currently unfortunately missing.
Okay. And then another question here, are other universities able to purchase these programs?
Yes, absolutely. I mean, these are not specific to Middlesex. If you're using bespoke software, for example, that you should be able to access these. In terms of remote access, we use a software called Splashtop. That gives us remote access to all of our specialist labs. In terms of setting up webcams, they're not proprietary software specific to Siemens or Festo. They're generic software that we use.
Okay, great. And probably final few questions now. So do you do any work with employers using these experiments? So linking with industry. Yeah.
It's early days at the moment in terms of working with employers. We haven't embarked on sort of these changes. We do sort of fault finding tasks with the, well, they're not necessarily employers, they're actually our industry partners. But in terms of repairing equipment, and we use the same technologies in terms of fault finding and repairing and troubleshooting.
Okay. Thank you very much, Mehmet and Luke from Middlesex University. That's fascinating, really amazing seeing the progress you've made during the COVID-19 era. Okay, thank you very much to both of you.
Thank you.
Okay, so now we come to the point where it's time to close for today anyway. So thank you very much to Helen, Freeha, Mehmet and Luke for such inspiring and interesting examples of some of the work you're doing in the higher education space. These examples will help us transform our society, engage with engineers with the necessary digital skills for our digital future. So from open STEM to digital apprenticeships to digital tools in teaching, digital skills are being learned and employed in higher education. These are just some of the many examples that have been used throughout the country. So if you have any case studies you'd like the IET to know about, please do email sep@theiet.org and a member of the education and skills team will get back to you. Please note all the talks today are online on YouTube and can be played back, will be able to be played back very, very soon. Feel free to share and rewatch them with friends, family and colleagues that may be interested. So we're back tomorrow. So looking ahead tomorrow, we'll have David Faulkner from Dassault Systems, who will discuss how the adaptation of tools engineers use can be harnessed by higher education to revolutionize teaching practices. We'll also hear from Martin Davies from the IET Academy. And then we'll round off tomorrow with Lisa Perkins from BT discussing how work between academia and industry can help nurture the next generation of technologists and engineers. So tomorrow is our industry day. We'll focus on how industry is helping transform digital skills through higher education. So I really hope you can join us tomorrow and enjoy the rest of your day and hopefully see as many of you tomorrow as possible. Thank you very much.